which is orthogonal to all these three decision plane or hyperplane that you have created. Okay, all the three hyperplanes that you have created, that is a vector W, which is normal to all the three hyperplanes. Now we are trying to derive the equation of the margin, and in this we are going to use a vector calculus uh, a concept, that projection of a vector A on vector B. Just a minute. Just a minute. Wait for 2 minutes. Okay. Again. So we are going to start with a vector calculus concept, that projection of a vector A on vector B is given by a dot product, that is a scalar product, vector A into the normal into the unit vector B. Okay, this is the vector calculus concept that we are going to utilize at this point of time. And if you say this normal value is equals to root of, for example, B is equals to B1 square plus B2 square, and so on. For example, B is in vector of the form B1, B2 up to Bn, then the magnitude of B, this form will be equals to square root of B1 square plus B2 square up to Bn square. Okay. For those of you who are not aware of this concept, just understand that this concept we are going to utilize in order to solve this particular equation. Only this one, you need to know this particular point, that projection of a vector A on vector B is given by this particular scalar product. Okay, dot product of two vectors. This it is how it is given. Okay, I suppose those who have some mathematical insight might know about this, right? Yes or no? Others need not worry. If you are not aware of this mathematical concept, need not worry. This one we are going to utilize to solve this particular one. Ultimately, you need to be aware of the equation only. Okay, but you need to be aware about the how we reach the particular equation. That's why we are going through the entire mathematical form, right? Okay. So just a minute. Okay. Okay, so for example, suppose we have a hyperplane such as this. Let us consider this is the hyperplane that we have. W transpose X plus B is equals to 0. And this is the decision boundaries. W transpose X plus B is equals to 1. And W transpose X plus B is equals to -1. Okay, and we have a normal vector W, which is orthogonal, that is perpendicular to all these three hyperplanes at this point of time. And now suppose we are taking two support vectors, and support vector in the positive side, that is X positive, and support vector on the negative side, X negative. And suppose we are drawing a vector from X negative to X positive. So this will be something like this, X positive minus X negative. This is the vector that we have. And suppose we are trying to find the distance of this particular vector. Let us say we have X negative over here. Okay. distance, we are trying to find the distance d. This is the margin distance that we are trying to find out, and we have a normal vector w over here. And suppose we try to project the vector x positive minus x negative on this vector w, then the distance d that will be the dot product of these two vectors. So it will be ultimately x positive minus x negative into w upon the magnitude of w. This will be the value of the distance between the two decision boundaries that we have created. Up to this, anybody has any problem? Is anybody having any problem? It is clear, right? So we have what we have done is we have taken two support vectors at this point of time, x positive on the positive side of the hyperplane and x negative on the negative side of the hyperplane, right? X positive will satisfy which equation? W transpose x plus b is equals to 1 will be satisfied by x positive because this is a support vector. This is a support vector. And x negative will satisfy which equation? W transpose x plus b is equals to minus 1 will be satisfied by this support vector x negative, right? Now, the vector that we have created from x negative to x positive, suppose we try to project that particular vector on this particular vector w, in this particular vector w, then ultimately, as we saw, the projection of two vectors, if we are trying to project a vector a on vector b, then the result is a dot product between these two vectors, which will be ultimately a into b upon magnitude of b. Okay, where this magnitude w value will be equals to root of w1 square plus w2 square plus wn square. And you know that what is w? W is the parameter. W is the parameter which we have in order to identify w and b. We are trying to identify in order to find the hyperplane equation such that the margin distance is maximum. Okay, right now. Okay, now suppose what will be the value of you can substitute the value of x positive and x negative over here. So if you see, x positive is going to satisfy w transpose x plus b equals to 1. So ultimately, w transpose x positive plus b is equals to 1 and w transpose x negative plus b is equals to minus 1. Yes or no? Yes, yes. Others are getting this point, yes or no? Okay, just a minute. Yes. So others are getting this point. So ultimately, x positive minus x negative will be equals to 2. So your distance value will be equals to 2 by magnitude of w. Yes or no? This is unit vector, so this value will be equals to 1. So ultimately, your distance value, the margin distance value will be equals to 2 by magnitude of w. Are you getting this point? Up to this, everyone is clear? Yes or no? Just let me know. Okay. Yes, Priyank, what is the doubt? Okay, yes. See how to see x positive is a point on the positive hyperplane. Okay, positive, the hyperplane that we have created, the decision boundary that we have created over here, and x negative is a point that on the decision boundary that we have created. Let me take another pen. Yes, x negative is a point. Let us say x positive is a point on this hyperplane and x negative is a point on this hyperplane. So ultimately x positive will satisfy the equation. X positive will satisfy the equation W transpose X plus B is equals to 1, and X negative is a support vector which satisfies the equation Wx plus B is equals to -1. So can you say that W transpose X positive plus B is equals to 1 and W transpose X negative plus B is equals to -1? Because the X positive is going to satisfy this equation and X negative is going to satisfy this equation, right? So now if you see X negative minus X positive, if you try to do, then this will be ultimately, okay, I forgot to mention one point is, this is the mod of this. You have to take a mod of this. So ultimately it will be giving you positive results only, right? So ultimately what will be happening? W transpose X negative is equals to -1 minus B, and W transpose X positive is equals to 1 minus B. Okay. So -1 minus B minus 1 minus minus of minus will be plus. So this 2 will be cancelled out. You will get 2 as an answer. Yes or no? Now is it clear how we are getting 2 as an answer? Yes or no? Okay. So ultimately your margin equation will come to something like this. It will be 2 upon mod of W. Okay. This will be the value, magnitude of W. This will be the margin value that you have to maximize. This is the margin value that you have to maximize. So are you getting the point? Now, so ultimately your optimization problem comes to this. What is your optimization problem? You have to maximize the distance. Maximize. Yes, D value needs to be maximized. Yes. Maximize the distance D is equals to 2 by magnitude of W. This is your margin value that you have to maximize given certain constraints. As you already saw, what was the constraint that was given is Yi into W transpose Xi plus B should be always greater than equals to 1 for all the data points. For all the data points. What is the data points here? Xi are the data points that are given to you, and the value of Yi into W transpose Xi plus B should be always greater than equals to 1. This constraint needs to be followed. If this constraint is violated, then this will not be optimization problem will not be solved. So you have to follow this constraint in order to solve this optimization problem. So ultimately your optimization problem is this for a case of support vector machine, and in the case of hard margin. What is the case of hard margin and soft margin? We had discussed in the previous lecture. In the hard margin case, no points in the positive side are allowed in the negative side, and no points on the negative side are allowed in the positive side. Even some of the points, some of the points can lie over here also. If you see, some of the points can lie, some of the negative points can lie over here, and some of the positive points can lie over here. This is not allowed in the case of hard margin. In the case of hard margin, all the positive points will be on the positive side of the hyperplane, that is after the decision boundary that you have created, and all the negative points will be on the negative side of the hyperplane, that is the decision boundary on the negative side that you have created. I suppose that is clear to everyone, right? Hard margin and soft margin concept. Yes or no? Okay. How we initialize the value of W transpose? Are you talking? So now the question Dave is asking is about optimizing the value. For the optimization problem, are you asking this question? Okay. Now I'm coming to that point actually. Okay, see. So far in the optimization problems that we have solved in the case of linear regression and in the case of logistic regression, if you recall, our optimization problem was unconstrained optimization problem. Unconstrained optimization problem. So far, we just had to minimize the cost function that was given to us. There was no any constraint given to us that given this particular constraint, you have to solve this minimization problem. There was no such cases here. But in the case of SVM, our optimization problem is a constrained optimization problem. Is a constraint optimization problem. Given the constraint that Yi into W transpose Xi plus B should be always greater than equals to 1. This is the constraint that you are given in order to solve this particular optimization problem. So now we are going to see. So if you, I would suggest all of you to go through one of the YouTube channels that is given to you, that is provided. That is IISc Bangalore numerical optimization theory. So in that particular videos, you will come in more insight will be given to you about numerical optimization. I cannot go in depth of this numerical optimization, but I can give you an idea that how we'll be solving this particular constraint optimization problem at this point of time. But if you want to gain more in-depth knowledge of how different optimization problems are there, and what are the conditions and everything, you may go through that particular YouTube channel, that is IISc Bangalore numerical optimization. Okay, for your reference, this is for your reference, for your greater insight. You may go through that for greater insight. Okay, so now as we saw, so far our optimization problems are unconstrained. Now we have a constrained optimization problem. One way to solve this particular optimization problem is you may convert constrained optimization problem into an unconstrained optimization problem. That is one way to solve this particular problem, which we won't be going through because there is a possibility that while converting the constraint to unconstrained form, you may not be able to solve this problem correctly. So we'll be going through a method to solve this constraint optimization problem, which is Lagrange multiplier method. Okay, we'll be utilizing Lagrange multiplier method in order to solve a constraint optimization problem. And how will be solving this? So right now, our optimization problem is to maximize 2 by mod of W given the constraint. Okay, we, for our mathematical convenience, most of the for our mathematical convenience, will convert this into a minimization problem. So if we are trying to maximize 2 by W, then we are trying to minimize W by 2. Can I say this? Yes or no? Can I say this or not? Yes? Okay, so ultimately we are trying to minimize W by 2 given the constraint by I into W transpose Xi plus B greater than equals to 1. Okay, so this is our optimization problem that we are going to solve. And we can also state this W mod of W as W square by 2. Why? Because magnitude of W is equal to root of W1 square plus W2 square plus Wn square. And we can also say that W, we can also call this W square of W. We can also call this square of W. I suppose everyone is clear with this particular point. Up to this, is everyone clear? Okay. What about others? Are others clear with this particular point that we are going to, that I just discussed? If anybody is having any doubt, you may please ask. Right now, we'll be going in a little bit in the mathematics part. So some of you, if you are facing any difficulty, please let me know so that in the classroom itself, we can solve it, right? So do not hesitate to ask any questions. Okay, so now, just a minute. Okay, so we'll be converting our problem, our optimization problem, into a Lagrange multiplier, which will solve our problems in a similar manner. Okay, the main idea of a problem is not changed, only that we are using Lagrange multiplier in order to solve this optimization problem. Previously, in the case of unconstrained optimization problem, we were trying to solve it using gradient descent. Gradient descent was one of the methods through which we were trying to solve the optimization problem. But in this case, since we have a constrained optimization problem, so this is a quadratic programming problem. If you see, this is a quadratic programming problem. If you see, I have converted my problem into minimizing W square by 2, and given the constraint Yi into W transpose Xi plus B is greater than equals to 1. I have converted my problem into this. So this is a quadratic programming problem which we need to solve using a Lagrange multiplier method. Okay, so what is the basic generalized form of Lagrange multiplier method is, we are converting our equation. This is our equation f of W. Let us consider this is our main equation f of W, and this is our constraint g of W. G of W is the constraint that is given to us. So our Lagrange multiplier form will be of something like this: f of W plus summation of I is equals to 1 to m alpha I into G of W. Okay, alpha I into G of W. Alpha I is known as the Lagrange multiplier. And why summation over all the summation from I to m? Because suppose we have n number of I is equals to 1 to m number of constraints, then m number of Lagrange multiplier will be used to solve this particular equation. Is everyone clear with the generalized form of Lagrange multiplier equation? Is everyone clear with this? Yes or no? Okay. So now how will we be solving this particular Lagrange multiplier equation? We'll be taking the first order derivative. We'll be taking the first order derivative with respect to all the parameters that we have. So what are the parameters that we have? We have W, we have B, and we have alpha, which is a Lagrange multiplier here. Okay, which is a Lagrange multiplier over here, and we'll be taking the derivative with respect to all of this, and we'll be equating equals to 0. And then based on that, we'll be finding out values of W and B such that this value, this optimization problem, that is W square divided by 2 is minimized. Okay, this value is minimized. Are you getting the point or not? Is everyone clear with this? How will we be solving this particular problem? Yes or no? Okay, so let us see one example for everyone so that it is clear. So for example, right now we can have we can have constraint can be of equality form and can be of inequality form as well. Okay, right now our constraint is of inequality form. What is an equality form of constraint? Suppose if yi into W transpose xi plus b was equals to 0, then it is known as equality constraint. And if this is less than equals to 0, then it is known as inequality constraint. Less than, greater than, these are known as inequality constraint. Right now we are, for example, right now in the example that is given to you, we are dealing with an equality constraint. Okay, so we are given, suppose, consider, right now I'm just solving a random example. I'm just giving you a random example so that you get an idea that how to solve this particular problem, right? And see, right now we are solving for a very small set of, we are considering that our data set is very small. But in the case of our data set will be very large. So in that case, our computer might have a certain quadratic programming problem installed in it, which will be solving this Lagrange multiplier problem in order to find your optimal solution. In this case, we are just considering for smaller set of database. We are considering what is the main idea, how it will be solved. We are just understanding how it will be solved at this point of time. Okay. So for example, we have to minimize a certain function f of x comma y. So f of function f is a function of parameters x and y, and it is given by x is equal to 2y, x plus 2y, sorry. And we are given to subject to a equality constraint x square plus y square minus 4 is equals to 0. Okay. So we will be converting it into a Lagrangian form, which is of the form L x y and lambda, which is a Lagrangian multiplier, x plus 2y plus lambda into x square plus y square minus 4. So here, what is f of x? F of xy is x plus 2y. That is our optimization problem that we have placed first, plus lambda into our g of w, which is g of w is our subject to constraint. That constraint that we are adding is x square plus 2y, x square plus y square minus 4 is equals to 0. That is the constraint that we are adding. Now we'll be finding out the first order derivative. So we have finding out the derivative with respect to all the parameters that we have, with respect to x, with respect to y, and with respect to lambda. So here we have calculated with respect to x, y, and lambda. And based on that, we are finding out the values of x, y, and lambda. These are values that we are finding. So right now, can you try to solve this particular derivative? Are you getting the similar derivative or not? Just try to find out, are you getting these values by solving this particular equation? What I want you to do is, right now this Lagrange problem is given to you. Can you solve this particular problem and give me whether you're getting this particular result, yes or no? Okay, I'm giving you 2 minutes to solve this. Okay, is everyone clear with this, what we are trying to do at this point of time? Yes or no? Just let me know in the comment, the chat section. Is everyone getting the idea what we are trying to do here? Okay. Okay. So what I want you to do is I want you to solve for this and let me know whether you are getting these values x, y for x, y, and lambda. Okay, I'm giving you 2 minutes. So this is the equation. Minimize f of x comma y is equals to x plus 2y. The subject to the constraint x square plus y square minus 4 equals to 0. Just let me know whether you are getting this value or not. And then we'll proceed to further points where we'll be solving for. Yes. Are you getting these values? Anybody got the values? Okay. Okay. Anybody done? Okay, yes, Kevin, what is the, are you getting the similar value that is stated in this particular slide? Are you getting values similar to this? Okay, fine. I suppose everyone is getting the idea. So based on this, what about others? Are others getting the idea or not? Okay, see, what we are trying to do is we'll be converting our optimization problem. Will be first step will be converting our optimization problem into Lagrange multiplier form, and then we'll be solving for the Lagrange multiplier. Now, right now, what we saw was equality condition. For example, if your conditions are equality based condition, our steps would be will be finding out the first order derivative, and then we'll be equating them to zero, and then we'll be trying to solve those particular equations that we have obtained. Okay, that will be case of equality based constraints if you have equality based constraint. Now, suppose if we have inequality based constraint, inequality based constraints means, for example, the one in our SVM problem, that is yi into w transpose xi plus b is greater than equals to 1. This is an inequality based constraint. In that case, what we'll be doing is we'll be following some other constraints, that are other conditions that we need to satisfy in order to solve the optimization problem, which are Korush, Kohn, Tucker, KKT conditions, Korush-Kohn-Tucker conditions that we need to satisfy in order to solve this particular inequality-based optimization problem. Okay, see, right now this might be getting a little confusing, but this you have to accept that you have to solve this particular problem. I suppose that everyone is clear that why we are proceeding for Lagrange multiplier. Since we have unconstrained optimization problem, so we are proceeding with Lagrange multiplier based problem. In that case, in order to solve an optimization problem with inequality based constraint, there are certain conditions that needs to be satisfied, which are Korush-Kohn-Tucker conditions, that are KKT conditions that needs to be satisfied in order to solve this particular Lagrange multiplier problem. Now, we are proceeding with one more point before going to the mathematical part of this whole idea, that is primal and dual form. Okay, primal and dual form of a particular equation. Now, what is why we are doing this is we have to solve for SVM, non-linear SVM also. In the later part of our lectures, we'll study something called non-linear SVM, in which we'll be identifying something called kernel trick. What do we mean by this is, for example, if you remember our XOR problem, XOR problem was something like this, where we had 4 data points, and we were not able to create a hyperplane to separate these points. In the case of kernel trick, what will be happening is we'll be converting our data set into another dimension. We'll be converting in the data set into a different dimension. For example, if you have a data set something like this, these are all positive points that we have in our data set, and suppose these are all negative points that we have in our data set. Now, in this case, a linear SVM will not come into rescue. Okay, for data set something like this. In that case, what we have to do, we have to use something called non-linear SVM, and in that case, we have to use kernel trick. We have to utilize kernel trick in order to convert these data points into another dimension, so that we can create appropriate decision boundaries. So, in order to help with this kernel trick, we have to convert our primal problem into a dual problem. Okay, what is a primal problem and what is a dual problem? Are you getting the point what we are doing in the case of kernel trick? I'm just giving an idea. We'll come to detail in the later lectures, but we have something called kernel trick in order to solve non-linear SVM. Whenever a data set is not linearly separable, or you cannot create a for example, a data set something like this, we'll be approaching to non-linear SVM, where we'll be utilizing something called kernel trick to convert them to appropriate form. For example, we may convert this into a polynomial form. We may use a polynomial kernel to create place this data set into a different dimension, and then we'll try to solve this particular optimization problem. Or there is another Gaussian kernel. RBF kernel is there. Okay, RBF kernel is there, where we'll be converting into some another equation we'll be utilizing to convert this data points into a different dimension to solve this particular data points. Okay, for that, we are converting our problem into from primal to dual form. Okay, what is a primal problem and what is a dual problem? Are you getting the point what we are doing in the case of kernel trick? I'm just giving an idea. We'll come to detail in the later lectures, but we have something called kernel trick in order to solve non-linear SVM. Now, what is primal and what is dual? Now we'll be coming to that point. Up to this, everyone is clear? Okay. So now what is primal form of an equation and what is a dual form of an equation? So if you see, our main optimization problem is to minimize w square by 2 given the constraint g of w. So consider this f of w, and given g of w is equals to something. For example, consider g of w is less than equals to 0, and there is some another constraint h of w which is equals to 0. Just consider for the example I am giving. So in all, our problem is to minimize the value of w, minimize the function f of w. For this, we have to find different values of w so that our function f of w is minimized. Okay, so this is our primal problem. This is our primal problem. Now we'll be creating a dual problem out of this. Which is in the form of a Lagrangian dual. Lagrangian dual, where we'll be solving for alpha and beta, and we'll be finding the solution for alpha and beta, which will ultimately give us the solution for w. Are you getting the point? So what is primal and dual form is primal form in which will be trying to minimize the value of f of w by finding different values of w and satisfying your equation. But in the dual form, what we'll be trying to do is maximizing f of w, Lagrange of this alpha, beta, and w for different values of alpha and beta. In short, if we solve for alpha and beta, we'll get a solution for w. So if we solve for this dual problem, we'll get solution for this primal problem. Are you getting the concept that I'm trying to explain here? Yes or no? Or it is not? Okay. See, first of all, what we are trying to do is we are trying to create okay. See, in order to solve your optimization problem that is given to you, that is w square by 2 and given certain constraint. Just consider that randomly we are given constraint g of w less than 0 and h of w equals to 0. These are some of the constraint that is given to us. And in order to solve your inequality based constraint Lagrangian multiplier problem, you have to follow some KKT conditions as well, where KKT condition states that all your Lagrange multipliers that you have in your equation, that is alpha, beta, gamma, whatever Lagrange multiplier you have, should be always greater than equals to 0. That is, their value should be always greater than equals to 0. That is one KKT condition that you have to follow in the case of inequality-based constraint Lagrangian multiplier. Okay. Now, our primal problem in this case, is to find the minimum value of f of w. Let us consider this value as f of w. Okay, and solve for this. Okay. So we'll be creating a Lagrange multiplier for this, and we'll be trying to find out different values of w and solving for minimize the values of f of w. Now, we can create a dual problem out of this. Eliminating w and b and creating an equation which is solely dependent on alpha, on the values of Lagrange multipliers that you have. So ultimately, a dual state of problem would be to maximize the values of alpha and beta. So ultimately, solving for maximizing the alpha and beta, ultimately solving for dual problem, we can find solution for primal problem. Are you getting the point that I'm trying to state here? Now it is clear. So what is the idea is, in mathematics, we have mostly, whenever you are converting your primal problem to dual problem, mostly your dual values are less than primal problem. But if you want to solve for, mostly in optimization theory, if dual values is equals to primal, the dual solution that you are getting, it will be equals to primal solution. That means if you are finding solution for your dual problem, then ultimately you are solving for your primal problem as well. So your primal problem will be solved if you are solving for your dual problem. Are you getting the idea now? Is everyone clear with this or not? Or just let me know in the comment. Okay. So I suppose everyone is clear with this idea. So what we are trying to do here is, in the case, in this particular Lagrangian multiplier cases, we'll be creating a dual Lagrangian problem for this. So ultimately what we'll be doing is, so we have L, W, alpha, beta. So now we'll be considering only alpha, since we have only one constraint, that is G of W, which is yi into W transpose xi plus b is greater than or equals to 1. So we have to follow certain KKT conditions as well in order to create this Lagrange multiplier. What we'll be doing is, we'll be, instead of minimizing f of w, we'll be trying to maximize this Lagrange multiplier alpha beta for alpha and beta. We'll be trying to maximize alpha and beta, and we'll be solving for this, which will ultimately give us the result for minimizing finding values of w such that f of w is minimized. Okay, that is what we are trying to do. We'll be creating a dual form of Lagrangian, dual form of this Lagrangian equation, so that we can solve for alpha and beta, that is the Lagrange multipliers that we have in our equation, so that ultimately we get solution for this. Okay, that is what we'll be doing. And why we'll be proceeding with this is, sometimes it is possible that your primal problem may not give you appropriate results. So we'll be so it will be easier to solve dual problem, and we'll see why it will be easier to solve dual problem instead of solving for the primal problem. We'll see when we will go through the entire equation. Now we'll go through the KKT condition that we need to satisfy for solving an inequality based constraint. There are certain KKT conditions that we need to satisfy. First is the first order derivative. Okay, first order derivatives that we have. First order derivative should be equals to 0. What are the first order derivatives that we'll be having? For example, the Lagrangian equations that we create with respect to all the parameters. For example, W with respect to B, and with respect to the Lagrangian multiplier alpha. And we'll be equating them all to equals to 0. That is one KKT condition that we have. Second KKT condition is, the value of Lagrange multiplier is always greater than or equals to 0. The third KKT condition is, the value of G of W will be less than or equals to 0. G of W, if you recall, is our constraint. Okay, G of W is the constraint that we have, which is yi into W transpose xi plus b is greater than or equals to 1. That is the constraint that we have. But we have to convert them into this form. That is, G of I is less than or equals to 0. And the last is, G of I into alpha I into G of IW will be equals to 0. This is another constraint that we have in our KKT condition. So these are the 4 KKT conditions that we need to satisfy. I'll be not going in the depth of why and how this KKT conditions are derived. That is a whole different mathematical concept, which you can study by yourself and understand. For your reference, you can try to understand it. That is IISc Bangalore numerical optimization. This YouTube channel is there, where you can go and try to understand these many concepts about numerical optimization for your understanding. Okay. So right now, these are some of the KKT conditions which you need to satisfy in order to solve inequality-based constraints and Lagrange multiplier, for the Lagrange multiplier. And we will come to the point where we'll be converting this Lagrange multiplier, which is in the form of W, to a form of alpha and beta. We'll convert this into a dual form so that it will be easier to solve. And why it is easier to solve the dual form, that will also come to the conclusion after we go through the entire solution. So now up to this, everyone is clear in this lecture, yes or no? Just let me know. We'll go through the derivation in the next lecture. But up to this, everyone is clear with today's lecture. Anybody is having any doubt? Okay. So if you have any doubt, you may also ask in the lab session or in any other on the next lecture, or you may email me as well. So do not hesitate to ask any questions in the lecture as well, right? And since this is a little mathematical in concept, so I would suggest that you go through some of the basics of derivative and a basic of Lagrange multiplier to understand this. We already solved one example of Lagrange multiplier where we'll be we'll be solving for this, and the main idea that we need to derive is after the derivation that we do. That's why we are going through the entire derivation, so that it becomes clear to you that why we are creating a dual problem out of this primal problem and solving the dual problem instead of primal problem, and why it will be easier. And also with the kernel trick, why it will be helpful in the case of kernel trick that we are going to use to solve the non-linear SVM that we have. So non-linear SVM is mostly whenever your data is not linearly separable. For example, one of the example that we saw, so we'll be converting using some kernel trick, that is some polynomial kernel or RBF kernel that we'll be utilizing to convert this data into another form, so that we can ultimately create decision boundary for them, right? So we'll be solving all these equations in the next lecture. So I suppose everyone is clear with today's lecture that we have done, right? Anybody is having any doubt? And we also solved for the margin. We also derived the equation of the margin and what is the optimization problem and constraint optimization problem, right? So I suppose everyone is clear with primal and dual form and why and kernel trick and the basic ideas that we discussed, right? Okay. Still, if you face any difficulty, I'll upload the PPT in 2 days. In one of the day, I mean, before Saturday, I'll upload the PPT. So in the next lecture, that is on Wednesday. So by Wednesday, you try to go through the PPT up to this point. You go through the PPT, and if you face any difficulty, you may ask in the next lecture. Fine. Okay. And I suppose everyone has shared with me all your lab work, and I have noted down that the names of those students who have not shared me the link and as well as who has not uploaded any work in the GitHub repository. So make sure that you update it and be prepared for. So I'll be doing the offline evaluation and will let you know for those of the students. So till that time, keep your repositories updated each week, right? So I'm ending the meeting now. And let us meet tomorrow in the lab session, right?